Hello everyone. For this tutorial I would like to discuss complex and imaginary numbers, which involve non-standard square roots, i.e. square roots that generally do not give you a valid answer because of how square roots work, but they are still useful in order to solve quadratic expressions that would normally be impossible to factor, as we will see shortly. In particular, we can represent the square root of -1 with a lowercase I, where I stands for imaginary number, as a reference to the fact that the square root of a negative number is usually not possible with normal numbers, as something squared always returns a positive number. Although technically all numbers are imaginary in the sense that they are abstract man-made concepts that are used to describe and predict certain things. So the square root of -1 is equally as valid as the square root of other things, depending on the situation we need it for. It is just referred to as an imaginary number because it breaks from the traditional norms of arithmetic. It follows that if we have a square root of a negative number besides 1, we can rewrite this as the square root of -1 times the positive counterpart. And we remember we can break a square root into multiple square roots instead of just one square root with all the factors under it. As in, square root of 12 equals square root of 3 times square root of 4, which you can convince yourself is true because remember the square root is simply an exponent where the exponent is 1/2. And we know that exponents multiply out in the same way that arithmetic numbers do. It follows next that because we defined I specifically as the square root of -1, if we square I, we get -1 exactly. Any imaginary number that has something more than I is called a complex number, as a reference to how it is a combination of imaginary numbers and normal or real numbers. And the general form of a complex number that works for all cases is a plus b times I, where a is called the real component, b is called the imaginary component, as a reference to it being multiplied by the imaginary number. Before we move on to specific problems involving working with complex numbers, we would first like to learn one more concept that is special to complex numbers called the conjugate, which is simply if you have a sum of two terms, one real and one imaginary, the conjugate is the difference instead, and if you are given a difference, the conjugate is the sum instead, so you simply flip the sign between the two terms. It should follow that even though I may seem bizarre from the way we usually think of something being squared, we can work with it as a variable similar to how x, y, and z we can work with as variables in algebraic statements, because of the fact the square root of a negative number or anything simply multiplies out like normal arithmetic as shown earlier. This means if we are given something like this, we can condense it to the most simplest form by doing subtracting -9 first, which means adding 9, and subtracting I next, which means we have 9 plus 4i as our answer in standard form. If we have problems involving I squared as part of our solution, we would do the appropriate substitution of stating that I squared is simply -1, which is not true for any other variable, unless we know a specific value for it. For example, if we are asked to simplify this, we would distribute the 7i. We would get -35i plus 14i squared. But since I squared is specifically defined as -1, we have 14 times -1, which means we have -14 as our real part of the complex number, and -35i as our imaginary part of the complex number, and we conclude that this is our most simplest answer. If we have something like this instead, we should remember how distribution works for polynomials, so we repeat the process, but use I instead of x, and so use the fact I squared equals -1 as a simplification when appropriate. So we do multiply 1 and negative 9 first, multiply 1 and 2i next, multiply negative 5i and negative 9 next, and lastly, multiply negative 5i and 2i last. We see we have I squared as part of our distribution, so we can do the substitution I squared equals negative 1, which we could not do for polynomials with x. So you multiply negative 10 by negative 1, you get positive 10. Negative 9 plus 10 is 1. So 1 is our real part of our complex number, and 47i is a simple summation of like terms, or terms of I, and does not involve any more tricky steps than that. So we get 47i as our imaginary part. Now that we are familiar with how polynomials work with complex numbers, we can see a neat trick for why we derived the conjugate earlier is, when you multiply a complex number by its conjugate, you get a real number, with no imaginary part, like this. We distribute as usual, we see it becomes 1 plus 8 times I, minus 8 times I, minus 64 times I squared. Negative 64 times negative 1 is positive 64. 8 times I and negative 8 times I cancel each other out. We conclude 1 plus 64 equals 65, with no and no imaginary part. So we can derive a more general formula / pattern is a plus b times I times a minus b times I is a squared minus a times b times I plus a times b times I, which cancels each other out, minus b squared times I squared, and b squared times I squared times negative 1 is the negatives multiply and cancel out. So we have positive b squared. We conclude that anytime we multiply it in this form, it will always become a squared plus b squared with no imaginary part, provided is exactly in this form, i.e. a complex number in its most simplest form and its conjugate. And if it is not, the formula will not work. One last interesting thing we should note before we stop discussing complex numbers is that because of how multiplication works, how exponents works, and how I is defined specifically as negative 1 when you square it, all of this gives us a pattern for when we raise I to an exponent. Namely, I equals I, which is already obvious. I squared equals negative 1 by definition. But when you do higher exponents, it becomes cyclic. So I cubed means negative 1 times I, or negative I. I to the fourth power is I squared times I squared, which means negative 1 times negative 1 equals positive 1. I to the fifth power is 1 times I, which is I. And we see now that we are back to I to the power of 1, or I, even though we have a higher exponent. So we conclude that the power of I repeats in this cycle every 4 exponents, which we can use to simplify complicated expressions that have higher powers of I than simply 1 or 2, which you may see in math classes. Now that we have discussed techniques to simplify algebraic expressions, we can talk about how to solve for exact values of x in algebraic equations next, starting with the most simplest type, which are linear equations, in the form a plus b times x. Known as that as a reference to how, when you graph out how the function behaves, you get a straight line. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.